Okay, so today is the 26th of April. How did that happen? And it's almost May. How many days, Lauren? 17 days. 17, okay. So, charge. You've spent the last day and a half charging things. Charge is an imbalance of electrons. You know, from what? Somewhere in middle school you learned that the subatomic particles have distinct electromagnetic charges. Protons are positive, electrons are negative. As long as you have equal numbers of those things on an object, it has no overall electrical charge. It is overall electrically neutral. When we have an imbalance of charge on an object, then we say that it has a charge. I should dig up the XKCD. For some bizarre reason, when people were first experimenting with when Thomson was finding subatomic particles and people were playing around with charge and current, electrons were designated as negative. We're kind of used to it anyway. Some things would be simpler if that were not the case, but it is, so we live here. If you want to charge an object positively, you have to pull electrons off it. You can do that. If you want to create a negative charge on an object, you have to add extra electrons to it. You did both of those today and yesterday. Yes, we've created charge. Yeah, you have. Charge is one more of those conserved quantities. Name me another conserved quantity. Mass. Mass is conserved. What other things have been conserved that we dealt with in the last chapter? Energy. Energy is conserved. Charge is also conserved. You can move charge all around. You can shuffle it around. You can't destroy charge. You can't create charge. And you already know this. Opposite charges attract. Like charges will repel. And that's one way to prove what charge we're looking at. You can transfer charge from one. Okay, so if we have a garden hose here. Does anybody remember this? People who had me for chemistry, you remember this? No? Okay. And we've got this hose that's full of water. And we add a drop of water to this end. Is that drop of water what comes out the other end? No. Some other drop of water. Yeah, some other drop of water does. That's how electrons on a conductive material work. Those electrons are just open to the idea of moving, and so if you add an electron to one end, you bump an electron off the other end. That's what conductors do. They allow the free movement of electrons. There are other materials that don't allow that to happen, and those are insulators. We use air is a really good insulator, actually. Ceramics tend to be very good insulators. Wood, carbon materials are good insulators. And rubbers, plastics, are good insulators. So you can charge either one of these by contact. If you put a source of electrons and connect it to something, you can get a material to take extra electrons usually. Conductors will take them more readily than insulators, but you can charge up an insulator. And there are two ways to do that. I'm hoping that tomorrow we will have the Van de Graaff generator up here. I'm looking around. Oh, you'll see. For likely suspects. Yeah, we've got a few likely suspects in here. You can do conduction charging. We have not done that yet. I'm hoping we will get to do that tomorrow. Conduction charging is where you have a neutral object and you put it in contact with another object that has excess electrons. The electrons flow onto the neutral object. Okay. So you could have charged your rods via conduction. If you had a rod that you were adding electrons to with your material, and you had grounded your hanging rod, and then you touched the two rods, electrons would travel from one to the other. The electrons flow off of one object onto the other, and when from one to the other, leaving each with an opposite charge. That doesn't make sense. The charge on two objects when you charge via conduction is identical. because you're just moving your charge carriers. You're moving your electrons. So I'm not sure. Yeah, scribble that out. Electrons flow from, well, one to the other. I think that word, if you, whoops, if you just take out the word opposite, it's fine. Leaving each with a charge. Okay, I'm not sure what happened there. And again, you have two objects that have the same charge at that point. You were doing charging by induction when you charged up one rod and held it near the other rod, repelling. You can get electron, well, actually no, because you weren't grounding. You could get that object to charge by grounding it. Who's heard the term ground, other than here? Okay, where have you heard it?
In cars.
In cars. Okay, when do you ground? When you're jumping a car. What do you ground to? Big metal, like the frame. You ground to the frame. Where else, who else has heard the word ground?
Computers.
Okay. Where do you ground? What do you ground? Why do you ground?
If you're building a computer, you want to make sure you're grounded, usually like to the frame of the computer.
Okay.
So that, because if you touch a part, you have static charge, which ruin the part.
Okay. My husband freaks out if he, for the first couple of years we were married, he did all the laundry because I didn't do it right. Me. He freaks out if you don't use fabric softener because he works on computers. He said, I cannot have charge. You're insane. Okay. But you don't want to build up static charge on yourself. You want to make sure you are grounded. What is ground? In the everyday colloquial sense, what is the ground?
Whatever you're standing on.
What you're standing on, what you walk on, the earth. In an electrical sense, ground is a giant reservoir. It is a reservoir of electrons. What's a reservoir? A storage area. We use it very often to refer to man-made lakes, created lakes, built lakes with dams are reservoirs. They are storage areas for water. They can accept additional water. Very often reservoirs have been created for flood control. They can accept additional water, and in times of drought, they're a source of water. So a reservoir both accepts excess of something and provides a source of something. When we talk about electronics and we talk about ground, the ground that we're talking about is a reservoir for electrons. It is both a source of extra electrons. It is also a place to stick extra electrons. So when we are going to charge by induction, we have a neutral object, and I like this image. It shows that there are both positive and negative charges there. We get this sort of partial charge initially by putting an object with the same charge near it. And then lo and behold, the electrons kind of all push to the other side of the object. You were doing this with the rods, you didn't know it, but as you were holding a charged object near one end of the rod, you were giving it a partial charge. If you then grounded it, while you've still got this object nearby, all those electrons flow off into the reservoir. They jump ship. What you're left with then, when you take away, the oppositely charged object, is you're left with an object that has some charge. Okay, that's charging by induction. Okay, I think I wasn't recording any of that. Polarization is something we can do mostly in insulators where they're not they're not well disposed to actual flow of electrons, so it's going to be hard to actually get electrons to jump ship. But you can get them to move around a little bit. So if you hold a charged object near an insulator, what you can have happen is the charges in the object will line up in a particular fashion. So they don't actually flow off the object because insulators aren't real okay with that, but they line up. And if you look at, for instance, this example, in the period before we ground that thing, what we have is really a polarized object. We have the electrons having flowed to one side of the object. And of course, this assumes that this is a conductive material, so they really flow. in polarization, they more or less just line up. We call this surface charge because the surface of the object behaves as though it is charged, but there's no actual imbalance of positive and negative charges. Here's where we will start to do a little bit of math. Coulomb's law, if you take your, whatever your intro physics part 3 course is, your electromagnetics course, you're going to look at Coulomb's law, and this is a way to describe the force, just force, and it can be attractive or repulsive between two charges. And when we talk about charges in this instance, we typically talk about these as point charges. That was a terrible little asterisk that I just drew. There. Just like we tended to reduce forces down to, everything, we have this, 45 kilogram kid on a 25 kilogram sled. We reduce it to a single point for the purposes of gravity acting on it and other forces acting on it. We do the same thing with charges. We reduce them to point charges. And it's easy because charge carriers are small. So we tend to talk about individual points of charge. Even if we have a big giant metal sphere that is charged, we talk about it as though it's a single little point in space. So we did not do Newton's gravitational law in here, but if you were familiar with that, gee, this looks an awful lot like it. What this says is that the force between two charges, and we have to have two charges here, is directly proportional to the magnitude of the charges. So the bigger the charge, the bigger the force, and inversely proportional to the distance between them. So the closer they are, the higher the force. The farther apart they are, the lower the force. This is the same law that you have for gravitational attraction between any two objects. What Newton's law of gravitational attraction says is that the force of attraction between two objects is directly proportional to their mass and inversely proportional to their distance. So we give that as force electric equals K sub C, which is Coulomb's constant. That's a constant. You have to use that one. Times the magnitude of charge 1 times the magnitude of charge 2 divided by the square of r, which is the distance between them. So we're going to do one problem together on page 636. One thing that I failed to mention, the unit for charge. So the unit for charge is the Coulomb, and I can never spell this right on my own. Yep. Coulomb. It is abbreviated as capital C. Okay. And it is a fundamental unit. There's no breakdown. It's not derived from anything else, though we're going to throw it into a bunch of derived things. Not recording. Okay. Coulomb's constant, 8.99 times 10 to the 9th Newton meter squared over coulombs squared. Newton meter squared over coulombs squared. So, what we need to know is the charge of the electron and the charge of the proton. Charge is given as Q in this. So the charge of an individual electron is negative, and it is negative 1.60 times 10 to the negative 19th coulombs. Let me get this all moved over so I can... Charge of a proton is positive 1.60 times 10 to the negative 19th coulombs. What's symmetry? Tiger, tiger, burning bright in the forests of the night. Okay, the distance between them was given to us. R equals 5.3 times 10 to the negative 11th meters. And we'll not worry yet about the gravitational. So I'm going to shrink this, stick it up here.
QE, Q1?
The QE is the charge of the electron.
But in
1 point.
the equation you wrote.
Yes, I'm sorry. Let me clarify that. So here we're talking specifically about an electron and a proton. We can do this with any two charged particles. So we typically refer to Q1, Q2, the first charged particle, the second charged particle. Doesn't matter which is which, doesn't matter who is who. It only matters that we have the charge of each particle. And you can also, if you know the force, you can figure out the charge on a particle based on the force. Okay, so the electrical force between them is equal to, let's shrink some stuff here. .99 times 10 to the 9th Newton meter squared over Coulomb squared times the quantity, negative 1.60 times 10 to the negative 19th coulombs. This problem looked particularly thorny. Why? All those exponents. Yeah, not a whole lot of fun. So if you remember my general recommendation for this, multiply all, do everything you need to with the prefix parts, then deal with the exponents. We have 8.99 times negative 1.60 times 1.6 divided by 5.3 times 5.3, that whole bloody mess, times 10 to the 9 plus negative 19 plus negative 19. Oh boy, I'm going to not have space either.
Got it.
You got it? Awesome. Minus negative 11 minus negative 11. That's not so bad. Okay, so I've got negative 0.8193 times 10 to the negative 7th coulombs. Or I'm sorry, this would be in newtons. This would be in newtons because this is force, electrical force. And oh, I always screw this up. Okay, so 8 point, how many do we have? 2? 8.1, negative 8.19 times 10 to the negative 8th newtons. Did I move my decimal right? Yep. Okay. And your book sig figs, of course, are always different. These problems aren't hard. They're plug and play. But very often we are dealing with a lot of exponents because we're dealing with very... Oh, and I see why. I see why. Okay. They disregard the sign here. Why would that force be positive? Is it an attractant force or a repellent force? They have opposite charges. Opposite charges? It's attractive. Yeah. So algebraically it comes out as a negative, but what you have to know is it's the magnitude of the charges.
Wait, so it's not negative then?
No, it's not negative. It's the magnitude of the charges, not their absolute signs. So that was my mistake. I should have gotten rid of that. Because what's going to happen is if you have two opposite charges, it's going to be an attractive force, and you just have to know that. So yeah, 8.19 times 10 to the negative 8th. Oh, we did have, the radius was given as, I'm sorry, the book sig figs were right for once. 8.2 times 10 to the negative 8th newtons. So it's very tiny, but it's very real. You can compare that to the gravitational force, which I'm not going to do. But if you look at that, the gravitational force between them is much, much, much smaller. It's 3.6 times 10 to the negative 47th newtons. And that would be an attractive force also. So they've got two things attracting them to one another. Okay. You have to look at the problem to see if it's positive or negative. What this means is if we have any two charges anywhere, we can figure out if the force between them is an attractive force that they're exerting on one another, or if the force on them is repellent. Here's the other piece that this means. We take something like this. This is 3-point charges, positive, positive, negative. We could figure out the force between all three of these as vectors and do a giant, complicated delightful, fun amount of math where we figure out the vectors of attraction and repulsion from each of those point charges. We're not going to do that. But I like talking about it because I like to see the looks on your faces. That is a possible thing. And if you go into electrical engineering, you do that because when you're designing circuits, you have to think about the forces that charges in one part of a circuit are going to have on another. Way, way, way beyond my pay grade. One problem that is going to be assigned here, actually two problems. So on page 636, this is 17A, problems number 1 and 4. Problems number 1 and 4.